Okay, here we are in section 3.2. Remember, chapter 3 is all about transformations, taking a function, and as we saw in the last section, we were shifting things left, right, up, down. Now we look at a different type of transformation called a reflection, and so this mirror is going to help us remember that in this section we're talking about reflections, and we're going to reflect things vertically and horizontally. So we can imagine what this function, say that this is f of x here, would look like if we, shifted it. Like if we shifted it up, it would just be this rigid shift up, or if we shifted it down or left or right. What we're going to do now, though, is we're going to reflect this function over the x-axis. What does that mean? That means that all of the y values are going to change into their opposites. So, for example, all of these points in the function over here have positive y values, right? Well, we're going to give them their negative y values. So we're going to reflect it across x, and it's going to look something like this for this part of the function. Now, for this part of the function over here, these all have negative y values. And so all of these negative y values are going to take on the same value, but just the positive value. And that part of the function is going to look like this. This part of the function has some more positive y values, so maybe this is a y value of 2. It's going to get reflected across the x-axis, and this y value of 2 is now going to become negative 2. And so this part of the function is going to get reflected, and it'll look like this. So the whole function will look something like this. This part will become these values. We're just taking each point of the function. Its x value stays exactly the same, but its y value takes on its negative, or the opposite value. If it was positive, it becomes a negative. If it was negative, it becomes a positive. And this new function is negative f of x. It's almost as if you took this original function and just spun it around the x-axis. All of the positives became negatives, all the negatives became positives, and they kept their absolute value, but they switched their sign. This function here, this expression here, you need to think of as the negative output of f at x. So the negative output of f at x. These are called vertical reflections. So whenever you see negative f of x, this is the function f reflected about the horizontal axis. So it's reflected, it's like everything gets twisted over this axis, and it's called a vertical reflection even though it's over the horizontal axis. It's a vertical reflection because all of the vertical components of the function, the y values, get changed to whatever their opposite value is. If there's a vertical reflection, there's probably a horizontal reflection too, and there is, and that's what we're going to look at next. So let's take the same function and let's do, instead of a vertical reflection, a horizontal reflection, which means basically for any point, you're going to look at its x value, its input value, and you're going to give it the opposite of whatever the x values, and the y values stay exactly the same. There's no reflecting the y values. We're just taking the x values and actually reflecting them across this vertical axis. So it's as if this is the axis that you're kind of spinning this function around on. So everything over here on this side of the y-axis is now going to come over here. And then everything over on this side of the y-axis is just going to have its mirror image over here. Okay, so let's see what this looks like. So we'll take this first little piece of the function and reflect it across the y-axis, do a horizontal reflection. And so we know we want to end up about right here. So that's that piece. And then let's take this whole big old chunk here and reflect it across, just spin it around that y-axis and reflect it across the y-axis. And so that part of it will look like something like this. And so this is the reflection. This here is the that's kind of a terrible picture. Let's see if we can clean it up a little bit. Give it more of a spine. Okay, but I think you get the idea that we've reflected this across the y-axis. Now, this new function, which is the reflection of f across the y-axis, it's called a horizontal reflection, is actually this function. So this is f of negative x. Essentially, you're switching off your x values for their opposite of the x values, and the y values stay exactly the same. So now we have something slightly different. We have the output of f at the opposite of x, at the opposite of our input. So this is definitely a new function. This is no longer your function f, but it's related to f. It's a variation of f. It's a reflection of your function f. You're going to take whatever your input is. You're going to say that it's right here. You're going to take like 2, and then you're going to say it's the negative of that. And oh, what's f doing at that point? That's what I'm going to do right here. So this new function, you could call it g of x, you could call it some other name. It's taking the output of f at the opposite of x. So any point, any value along here, say -3, this new function says, okay, to find my value, I'm actually going to hop on over to the opposite x value and find out what f's doing at that point. And okay, it's down here. Well, that's what I'm going to be right here then. Okay, right here for -4, I'm actually going to hop over to the opposite of -4, which is 4. See what f is doing at that point. Oh, it's down here. Okay, that's what I want my value to be right here. So this new function looks at the opposite x value and finds out what f is doing there. So we say that for horizontal reflections, f of -x is f reflected about the vertical axis. And we should be sure to note, these are new functions. They're not the function f anymore. This is a different function. It's definitely, keying off what f is doing. It's like the kid brother or the kid sister of f, who wants to be like them, but in a different sort of way. So they're kind of saying, well, what's f doing at this point? Okay, I'm going to do that at the opposite point. So these are, both of these functions are new functions that are variations of the function f. Let's just review so far the transformations that we know. There are a couple more we're going to learn, but let's just review what we've got so far. These were the 4 that we saw last time. These top 2, think to yourself, is this a vertical shift or a horizontal shift? This first one is definitely a vertical shift up 3. Here, right here, we have a vertical shift down 3. And then these guys must be the horizontal shifts. So okay, we got to think. This is always the opposite of what we think it should be when it's a horizontal shift. Oh, we got to switch that too. So this one is a horizontal shift. And we want this to be going left 3. And then the only thing left is this will be a horizontal shift to the right 3. And then these are the 2 new ones we learned today. This reflection around the x-axis, so it's actually a vertical reflection, and this reflection about the y-axis, which is a horizontal reflection. For our third example, we're going to look at this function. This will be sort of the parent function, f of x equals x cubed. And the graph of that looks something like this. I'm going to define a new function, g of x, and g of x is going to be f of -x plus 7. And the first thing we're asked to do is graph g of x. And we've definitely got a couple things going on here. G is going to be a transformation of the function f, and this is going to be some sort of reflection. Looks like it's a horizontal reflection, so reflecting about the y-axis. And then we have a vertical shift up 7. So if we're going to graph g of x, it's got the same basic shape as f, but we need to perform this reflection, and so that will cause it to look like that. And then we need to move everything up 7 units from there. Both the reflection and that vertical shift both need to happen. And when I perform that reflection and then the vertical shift, I'll get something that looks like this. The vertical reflection happened. It's as if, sorry, the horizontal reflection happened. It's as if I spun it around that vertical axis and then I shifted everything up 7 units. So horizontal reflection and a vertical shift. The second thing I'm asked to do is to write the formula for G. So we know that G has this relationship with F, but we'd like to have a formula for G that is independent of F, just G and some input where we don't reference back to F. So let's see here. G of x equals f of negative x. So this is at least the beginning of it. And f is this guy, x cubed. So g of x would be not x cubed, but how about negative x cubed? Because in g of x, we take f of negative x. That's the first part. And then we also have a plus 7, so we want to add that on to the formula also. So I think we have all the pieces. We've got, this is f of negative x plus 7. And we can clean up this guy a little. If you take a negative x and you cube it, let's see, that would be negative x times negative x times negative x. So that would just be negative x cubed plus 7. The parentheses are gone because that negative sticks around through that cubing. There's 3 negatives, so you still have 1 left over and you can lift the parentheses. And this is it. We've done it. They've asked us to graph it. We graphed it. And they've asked us to come up with the formula for G. And we've done that here. Our next example, we've got this sort of parent function f of x equals 2x plus 3. And already in your head, you know what this looks like. This is the form of a linear function. So it's going to be a line with slope 2 and a y-intercept 3. So we can already kind of sketch out what that will look like. It'll be something like that. And then we have this transformation of that function. G of x is going to be negative f of x plus 5. And so we can start to think what each of these little pieces of the transformation are going to do to it. This will be, let's see, this will be some sort of horizontal shift, so to the left 5 units. And then this will be this reflection, a vertical reflection, or a reflection about the x-axis. But the thing that they ask us to do first is find the formula for G. So we can do that. So I'll probably take a couple steps to do this. But let's think. G of x is negative f of x plus 5. So for right now, I'm just thinking about the algebra of this. I'm not really thinking about what the graphs are doing. But if G of x is negative f of x plus 5, and f of x plus 5 should be 2. Well, it's not x anymore, it's x plus 5. That's our input. X plus 5 plus 3. So this negative is just coming from this negative. And then f of x plus 5 tells us, okay, my iPad died there for a minute, so I'm not exactly where I left off, but we have our negative here, and then f of x plus 5 is just this right here. It's x plus 5 as an input to the function f. And so really we're just going to clean this up and we'll get the formula for G. And as I clean this up, it'll become negative, let's see, 2x plus 10 plus 3, which is just negative 2x plus 13. So G of x is negative 2x minus 13. And now let's go ahead and graph both the original parent function and then this transform function on one set of axes. And my original function f it goes through the point 0, 3 and has a slope of negative 2. No, has a slope of 2. So it looks generally something like this. So here's f of x. And then g of x has a vertical intercept of negative 13 and a slope of negative 2. So looks something like this. So then we need to ask, is it reasonable that this f of x, the parent function, once it went through this transformation, should look like this? And it is reasonable. The first thing that happens is a shift left 5, and then we do this reflection about the x-axis of vertical reflection. So this guy gets shifted left 5 units, and that shift will make it look something like this. And then it gets spun around the x-axis, and once it gets spun around the x-axis, it takes on what this looks like, g of x. So both those transformations resulted in this new function, g of x, which is a derivation or a variation on f of x. Also in this section, we get the opportunity to get a little more confident using tables and function notation. So we're going to look at 3 or 4 examples here using this table here. And the first one is this is really just practice with function notation, but you'll notice that a lot of these, like this, for example, this is a reflection, but literally in this example, we don't really need to even know that that's a reflection. We're just going to get more confident with this function notation. So the task is find negative f of x when x equals 1. So if we know that x equals negative 1, we literally are just going to put that in as our input into this function. And so we're really looking for negative f of negative 1. Okay, and all we have to go off of is this table. So let's see, our input is negative 1. So which column do we want? Well, this is an input, and this is our input column. So we go down to negative 1. And we evaluate the function at negative 1. So f of negative 1, this part, is 2. So the negative we haven't done anything with, but this part, f of negative 1, is 2. We just read that straight off of the table, that f of negative 1, the function evaluated at negative 1, is 2. And the negative just kind of came along for the ride. Okay, but essentially at this point we're done. I mean, we found our answer. The answer is negative 2. Okay, so more practice with function notation and using tables. So find this big old honkin' thing when x equals 2. Okay, we're just going to attack it a piece at a time. So find this when x equals 2. If x equals 2, then I'm going to put that in for x right here. That's going to be my first step. So f of, let's see, negative x, but x is 2, minus 2 plus 1. And that should be f of negative 2 minus 2 is negative 4 plus 1. Okay, so could I say this is just negative 3? No, because we have this negative 4 and the 1. You can't combine those yet because we have to evaluate the function at negative 4. So this is where I'm going to use the table. And I go to the table, and when my input is negative 4, what is my output of the function? So when my input is negative 4, my output of the function, f of negative 4 equals 12. So f of negative 4 equals 12. F of negative 4 is 12, and I still have this plus 1 hanging around, so the answer to the whole thing is just 13. In section 3.2, these types of problems seem to be what trip students up the most. Let's look at one more example to get some more practice with this. Okay, this is a slightly different type of problem. Instead of just finding some expression, we now have an equal sign here, and we're asked to solve this equation. So we're just going to take things a piece at a time and see what we can see. F of negative x plus 4 plus 2 equals 7. Well, I can't really pull that one out of my brain right away, so what I'm going to do is just try to clean things up. This is all one block. I can't separate this yet, but I could move this negative 2 over to the other side and combine it with the negative 7. It would be like subtracting 2 from both sides, so I can do that. So this stays as f of negative x plus 4 equals 2 minus 2 drops out, and I have just 5. Okay, I'm still a little bit unsure, but I know that the function evaluated at some point equals 5. So I'm getting some sort of output as 5 for some sort of input. Well, what input gives me 5 as an output? What input gives me 5 as an output? Do I ever get 5 as an output? Yeah, I do right here. So there was an input, it was 3, that gives me 5 as an output. So in other words, I know that f of 3 equals 5. Well, I also know over here that f of negative x plus 4 equals 5. So whatever's in here must equal 3. And this is a big, this is kind of the big cognitive jump in this problem. You have to recognize that what's inside here must equal 3 because it's both of those are yielding an output of 5. And so at this point, once we make that realization that, oh, okay, negative x plus 4 must equal 3, that's easy to solve. So negative x equals, let's see, 3 minus 4 is negative 1. So x equals 1. And that's the solution to this problem. So a few more steps involved there, and from here to here, we definitely want to be sure we think through what's happening and why that was the right way to solve this problem. Last part of this section, we need to talk about some special symmetries that we'll come across. The names of these two symmetries that are really special are called even functions and odd functions. And f is an even function, or f is even if f of x equals f of negative x. Think about what that means, that the function equals its reflection across that y-axis, so its own horizontal reflection. Can you think of a function, a picture of a function, that if you twisted it around the vertical axis, it would look exactly like the original function? Here is an example of an even function. You can imagine if you were going to twist it around this vertical axis that you would get the exact same function. So the function itself is equal to its horizontal reflection. And remember, a horizontal reflection means to twist it around this vertical axis. So what about this guy? Would this be an even function? If we twisted this function around the vertical axis, would we get something that looks exactly the same? No, we're going to get something that looks different. It's going to look like this. So we get two different functions. So in this case, this function is not even. So when you see the word even, you know that that's a function that is symmetric about the vertical axis, that twisting it around the vertical axis would yield the same exact function. And we call f an odd function. So f is odd if f of negative x equals negative f of x. So that's a little bit more to it than just even. Even's a little more basic. But here we have a function where if you had an original function, the horizontal reflection of that function would be equal to the vertical reflection of that function. And the one we just looked at that we said wasn't even is actually an odd function. So this function here, let's see, this is an odd function, and I'll show you how that happens. So an odd function basically is you take an original function, you reflect it vertically, or if you reflect it horizontally, you would get the same thing. So let's do both of those. Let's see, if we took this and reflected it across the y-axis, we would get this, right? Just twisting it across this axis. Okay, so let's twist it across this axis though. Let's see, this would come up here, and then this would come, okay, interesting. We get the same exact thing as if we were going to twist it around the vertical axis. So this situation happens if when you do those, either a vertical or a horizontal reflection, you're getting the same thing. And we say that this is symmetric about the origin. So odd functions are symmetric about the origin. And a good question, odds are maybe a little bit trickier to see than even functions, but a question that you can ask yourself is, if I reflect it vertically or if I reflect it horizontally, when I do either of these, do I get the same thing? And if you do, then it's an odd function. Not the same thing as the original function, but the fact that the reflection, the vertical reflection and the horizontal reflection are equal, then that is an odd function. And then we definitely need to note that a function can be neither odd nor even. Often a function is neither of these things, and you can look at this function. This is neither even nor odd. Think for a minute what the reflection around the vertical axis would be. It would be something like this. And to be even, it has to match the original function exactly. It definitely doesn't do that. So if this is the horizontal, or the horizontal reflection, and then we had a vertical reflection, well, the vertical reflection is something like this. To be odd, these two blue functions need to be the exact same function, and they're definitely not. So this is an example of a function that's neither even nor odd. Okay, so our big ideas here are, we talked about vertical and horizontal reflections of f, just continuing our series of different types of transformations of f, and we got some good practice with tables and function notation, evaluating different things, or even solving certain equations using a table and function notation. And we introduced the idea of an even odd functions. We won't really talk more about these, but we definitely want to be able to recognize them and even construct them if you're given a function, draw the graph of its even function, for example.